Good. Now that we talk about, authenticated encryption and, mentioned the competitions, let's talk about Ascon, who was one of the finalists in Caesar competition and who also won NIST lightweight lightweight cryptography standardization competition. So Ascon, designed by Dobranik, Eisleder, Mendel, and Schlaffer. It is a sponge construction. Block size is 64 or 128 bits. This is important because when they submitted to the NIST competition, the block size 64-bit was their initial choice. But in the document, they also talk about the alternative version when the block size is 128. So until the end of the competition, we always focus this part because it is the main design. But after the competition and when Ascon won, NIST talked to the designers and said that they want to standardize the 128-bit version because this increases the rate and doubles the speed at the end of the day. So internal state is 320 bits. Key size is 128 bits. This is also important because in the Caesar competition, there was the initial version, which also supported 96 bits. But actually nowadays, it should be considered small and not be used. So this is why they eliminated this version. Nonce is 128 bits. Tag is 128 bits. Number of rounds depends on which phase of the authentication you are doing. If it is initial or the final part, it is 12. If it is the encryption part, it is 6 rounds. So everything will be more clear in the following picture here. And these are some properties. Okay, so it's a single pass, online, inverse free, security proof. It has because it's a sponge function. It is lightweight, fast in hardware and software. No table lookup. This is important. For instance, SBox operations. If you go to the table, then it's it's might be a little bad for side channel attacks. So this is why they don't use any table lookups, but they still use an SBox. So I will explain how this can be done. Okay, so this is the general picture. So assume that you have an internal state of 320 bits. So initially you fill it with IV, 64 bits, secret key 128 bits, nodes 128 bits. So initially you have 320 bits. So they are represented as 5 rows of 64 columns. So each rectangle here represents a single byte. Okay, so imagine this is your internal state. So at the top row, you put your IV. X1 and X2, 128 bits are your secret key, and the bottom 2 rows are your nodes. Nodes is just a random value that is, used only once for each communicating messages. Okay, so initially you fill it with this, then you perform the permutation operation, P, which actually consists of confusion and diffusion layers. A many times, and as you can see, A is 12. So as the initialization, you perform this operation 12 times. So you kind of mix the, IV key and the nodes. Then there's an XOR operation here, as you can see, zeros filled until the 128-bit secret key. So you XOR it here. As you can see in the future, I will XOR it with something else. This is what I mentioned, domain separation. Okay. With these different XOR operations, you actually separate this part with this one and then this one. Okay. Because then if they didn't exist, you could take this dashed line and put it here. Okay. But you will have the same result. Okay, so this is the initialization part. Then if you have associated data, recall that associated data is the data that you don't encrypt, but they still affect the tag that you are going to produce at the end. So if you have this kind of data, you feed it and perform permutation B many times, which is 6 this time. If you have more blocks, you do it, etc. As you can see here, you see the letter R and C. R is the rate, C is the capacity. So if you use the block size as 64 bits here, then R is 64 bits. C is 320 minus 64. Which should be 192, if I'm not mistaken. But if you choose block size 128, which actually was chosen by NIST, then C will be, 320 minus 128. Okay. No, okay. So when R is 64, this is 256. When R is 128, this is 192. Okay. Good. But if there's no associated data, you can simply erase this part. Okay. So let's come to the encryption. So R bits at a time. Again, let's assume that it is 128 because that version is finally standardized. So you XOR your 128 bits of your plain text to the top 2 rows here. Okay. Then the results of these top 2 rows are provided as first ciphertext block. So you can think about it like this. So you have an internal state which the attacker has no idea about. But when you want to produce first ciphertext, you kind of reveal this 128 bits because it is just if you XOR P1 and C1, you obtain the top 2 rows of your internal state. But then you mix it again by performing this permutation operation so that you kind of hide it again and again and again. So you do this, encryption operation until you run out of plain text blocks. Then you perform the final permutation and XOR your secret key to produce your tag. So as you can see, you provided the ciphertext here, tag here. So it provides both encryption and authentication, authenticated encryption algorithm. So, but I haven't talked about what P is, right? So let's focus on this permutation operation. So as I told you that the internal state is represented as 320 bits like this. So that's P operation consists of first adding round constants, which only affect this 8 bits, I guess. Right. So if it is round 0, then you XOR it with F0, 1, 1, 1, 1, 0, 0, 0, 0. And in the next round, it's just 1 minus this and 1 plus this, etc. So adding constants actually, in terms of cryptography, it doesn't provide any confusion or anything, but it breaks the symmetry in the cipher. Okay. Next step, performing SBox operation. So recall that we have 5 rows. So if you take this 5 bits of a column, then you need a 5 by 5 SBox to write it back. Okay, so this is the 5 by 5 SBox of Ascon, which is actually a modified version of Ketchak's SBox. Okay, this is a deliberately chosen SBox. It is not the best 5 by 5 SBox in terms of security, but this is kind of one of the best in terms of both performance and security. Because when you have these 5 bits, you can represent them as 5 bits like X0, X1, X2, X3, and X4. This SBox is just a function that takes 5-bit input and provides 5-bit output. So you can write the output as Y1, Y2, sorry, Y0, Y1, Y2, Y3, and Y4. And actually, you can write this YIs in terms of logical operations on XIs. Okay, so instead of performing a table lookup, you can write the values of these bits by performing those following logical operations that I mentioned. And I think there are like 21 operations you need to perform on these XIs to obtain these YIs. So instead of a single table lookup, you perform like 21 or 22 logical operations. So you might say that this is a little bit more costly. Instead of a single table lookup, I perform 22 logical operations like XOR, NOT, and etc. But the good thing is that generally you are going to do it on a processor that supports 64-bit operations. So your first row actually contains the first bit of each SBox value. So the 22 logical operations I mentioned to you, instead of performing them on this single column, you can actually perform them in parallel if you take your X0 as the first row, right? So in 22 logical operations, you perform 64 SBox operations in parallel. So this way, you don't use any table lookups, so you don't worry about timing attacks. But also, instead of performing 64 table lookups, you simply do 22 logical operations on 64-bit value lookups. Okay, so this is the nice thing. This is the one I'm going to do in the implementation. So please watch the video and understand how I do that. Okay, so this is the good thing. But as you can see, this is the confusion layer. It only works on the columns. So I need to perform some diffusion on the row level, and this is what they do. So they perform operations like sigma 0, sigma 1, etc. So you take the top row x0 as the input, and the output is x0 XOR with x0 rotated right to 19 bits, XOR x0 rotated to 28 bits to the right. So this is an easy operation. So as you can see, this is a single round. Let me recap. You start with the round constant XOR, perform 64 SBox operations in parallel, which can be done in 22 logical operations. Then you take each row and XOR it to itself in a rotated way. So as simple as that. As you can see, this will be super fast on many architectures if they especially support 64-bit words or 64-bit operations. Okay. So if I go back, this is what is inside this P. So this was a single round. You do it 12 times here, 6 times here, and 12 here. Okay, so very nice, very fast, very compact, and easy to implement algorithm. This is why I actually implemented in the lectures. But as you can see, I still made an error. So in the videos, I took this constants from the document. I copy-pasted it. I took this first part. Then in the video, I focused on something else, and I forgot to copy-paste this part. So these constants, since I didn't wrote it there, depending on the compiler, either the compiler thinks that those array values are 0, which generally is the case, or they will not assign them to 0. So whenever I call those values, they will simply fetch what is inside the RAM, which might be a random value. Okay. So this is why my implementation in YouTube is not correct, because I don't use this constants, this part. Instead, most probably the compiler thinks that they are 0. So it's a good actual lecture to show you what kind of errors you can make when you implement a cryptographic algorithm. But as you can see, it is a very nice and very compact algorithm. So it is super fast. And here you might ask, why not increase the R more? For instance, why not make it 192 bits so the C capacity becomes 128? So in sponge functions, the security proofs only work when C is 3/2 times of R or larger. Okay, this is why you take it 192 and this is 128. Increasing rate any longer means that all of those security proofs or sponge functions no longer work for you. This is why it is kept like that. Okay. So please watch the video and see how you can implement Ascon in C. Okay. Good. I stopped the recording again, and actually this